Last lecture, we started with Maxwell's equation, and we talk about in the vacuum case, where there are no free current and there are no free charge, and we found that the electric field and also the magnetic field, they both satisfy the wave equations, and also the electric field and the magnetic field, there really is a wave that are propagating, with a speed of light. Okay, so in other words, that light is really an electromagnetic wave. So this is a very important prediction, from Maxwell's equation, which was experimentally, verified. And then from there, we then discussed about the energy, the momentum, and also the flux density, that are carried by the electromagnetic field. Okay, and then we discussed that if wave can also propagate in matter, and there is only is also the same equation. Assume there are no free charge, no free current, and it also satisfies the wave equation, and only the speed is really reduced by a factor of n, which is really the index of refraction of that material. And then we talk about that the wave can be propagated from one material to the other material. So that one we really need to use the boundary conditions to figure out what is the reflection and what is the transmission. Okay, so let us discuss about that now. So let us assume I have XYZ position here, and we have a surface here. Okay, just on this with this z equals to 0. Okay, so there is a surface. So left side is some different material, and the right side is another different material. So now we have a wave. Okay, let us consider is monochromatic plane wave. Okay, the wave is coming, just have the normal incidence to this surface. Okay, so now let us consider. Now we have we call it EI, means the electric field for the incident wave. Okay, now we have BI. Let us consider this way. Okay, one is x direction, one is y direction, and we know that the wave is propagating with a speed of v1 along the z direction. And we say that on this surface, okay, so then we will have reflection, and then we will have the transmission. So let us say for the transmission wave, okay, let us put it as ET. This is the electric field, and this is the magnetic field, and the speed with, moving with the speed of v2. Okay. So now here we also have reflection. So we have ER here, okay, and the wave is really propagating. V1 is being reflected that way. So you will find that BR should be the reflected magnetic field direction should point into that way. Okay, so this is what we have. Okay, so this is the reflected wave, so this is the transmitted wave, and this is the incident wave. We can write it down as EI, the incident one. So we have E0. Okay, EI, of course, let us depends on Z, depends on T, because this is a plane wave. So we have the magnitude, and then we have K1Z, okay, minus omega T. Okay, we said we assume it's on the x direction. Then we have the magnetic field, okay, B0 II K1Z minus omega T. Okay, so we mentioned that they are in phase, so they should like that. Okay, so this is the incident wave. Okay, now we consider transmitted wave. Okay, so transmitted wave. Okay, so this is E0 transmitted. This is amplitude, and so here the wave number is different. It's K2 now. Okay, the direction is omega t. Okay, x hat. Okay, as I said, the component, the phase could be different. Okay, but that phase is included here, which is really a complex number. So it's often, if you really is E0t, this is a real number, times this delta, for example, indicated the phase for the transmitted wave. Okay. So then we have this, so here, because B0 is really related to E0, okay, it's just divided by C. Okay, so we just simplify that. So here we also have this E0t divided by C EI K2Z minus omega t. Okay, so this is for the transmitted wave. So then we also have this reflected wave. Okay, so this reflected wave is ZT. Okay, it's really the reflected wave. Okay, remember now it is really propagate along the minus z direction, and we said we described before, for waves that are propagated in the negative z direction, we only need to change the sign, and we don't need to change this omega t1. Okay, so it's really just like that. Okay, so we also have for the magnetic field. Okay, so this is E0R divided by C. Okay, divided by V1. Okay, sorry. So this is I should really, this is not a C. Okay, we can consider V1, V2. Okay, so this is V2. Okay, and V2. So this is a V1. Okay, because it's in the first material. Okay, then we have EI minus K1Z minus omega t, because it's in phase with the electric field, but this is moving as minus y direction. Okay, so this is what we have. Okay, so then what do we really have that now we use these boundary conditions, okay, that we described before. So what do we really, you look at the equations I showed at the end of the last lecture. So we really have this E0 and reflected must equals E0t, on this surface, left side electric field and the right side electric field. And then we have, look at the equation that I derived before. So this is for the magnetic field. Okay, so V1 is 0R. Okay, so this is really, you can think of the B1 from the left side equals to, this is the B2. So this is the B2 on the right side. Okay, so their relation is 1 over mu 0 B1 equals to 1 over mu 2 B2. So these are the equations that we have. Okay, so now we just plug in, the formulas that are listed here, and I will not do all the calculations. I just wanted to show you it looks like this. Okay, for the transmitted wave, okay, for the reflected wave, it's proportional to the incident wave. Okay, and there is a factor which is 1 minus beta divided by 1 plus beta, where beta is really defined as mu1 V V1 divided by mu2 V2, okay, which if you put a index of refraction, which is N2 divided by N1, okay, so this is the beta value, okay, the reflected wave and the incident wave, okay, and also the transmitted wave, okay, is really also proportional to the incident one, but is related to a factor of 2 divided by 1 plus beta, okay. And we said that for most cases, mu1 and mu2, they are close to each other. So this one is really proportional to V1 over V2 is really equals to N2 over N1, okay. Because mu1, mu2, they are often close to each other. Okay, so if we do that, we really find that is U0R is really roughly is V2 minus V1 divided by V2 plus V1 is 0, 1, okay. The transmitted wave, okay, equals 2 V2 divided by V1 plus V2 is 0 I, okay. And here just to show you what is the amplitude of the reflected wave related to the incident wave, what is the transmitted wave amplitude related to the incident wave amplitude. And if you remember that we described the case for one-dimensional wave before, so you see that this is a very is actually identical to the ones that we described before, okay. And also, if V2 is greater than V1, so this is becomes a positive number, so the reflected wave will be in phase with the incident wave. And then of course, if V2 is less than V1, so then the reflected wave will be out of phase with the incident wave, okay. And for the transverse one, transmitted one is always in phase, okay. And then we can also the amplitude change, okay, the absolute value, okay, is really just this is just the absolute value, okay, V2 plus V1 is 0 I, okay, so which is really N1 minus N2 divided by N1 plus N2, okay. Okay, E0T, the transmitted one, is 2V2 divided by V1 plus V2, E0 input, incident one, N1 plus N2, E0I. Okay, okay. And also, so this is really, if we talk about the reflection coefficient, what is the amount of energy in some sense. Reflection coefficient. This one is really E0R divided by E0I, okay, square, okay, because this reflects the amount of energy reflected. Okay, so this one will give us N1 minus N2 divided by N1 plus N2 square, okay. We also can define this so-called transmission coefficient, okay, which is the transmitted amplitude divided by the incident one, okay. So this one becomes 4 N1 N2 divided by N1 plus N2 square, okay. So it becomes like that. So from here we get R plus T equals to 1, which is certainly should be the case, because the energy is conserved. The incident wave energy should equals to the energy, the sum of the energy, for the transmitted wave and also the reflected wave. Okay, so let us consider, if we have a light pass this, let us say this is air, so this is glass, okay. So N1 is roughly 1 here, N2 is 1.5 here, okay. So if we have light that are coming from the air and that shine on the surface of the glass, so what you'll find that R is really 0.04, and T is equals to 0.96. Okay, so you can see that 96% of the light will be transmitted, while only 4% of the light will be reflected. Okay, so this is what you can see from this. Okay, so for this I just if you learn this advanced electrodynamics, there are a lot of calculations that you need to do. So here I just show you these very simple ideas, how to calculate the reflection and the transmission, and as I said, more complicated calculations, you will learn from graduate schools. Okay. So now I want to just talk about the last topic. Okay, is to talk about the gauge transformation. Okay. Okay. So remember that for the Maxwell's equation, okay, we have this del dot E equals to rho divided by epsilon 0. We have del cross E. We have del dot B. We have del cross B. Okay. So this is the equation, Maxwell's equation we have. Often, for these are just the equations. We often tell you what is the rho distribution, what is the J distribution, and we want you to use these equations to figure out the electric field, and we want to figure out the magnetic field. That is almost, all we have to do, for the electromagnetic problems. Okay. So for the static case, we can just use Coulomb's law and Biot-Savitz's law, okay, to find out. Give us rho, we can find E. Give us J, we can find B. Okay. But the problem is, for the time-dependent ones, okay, we cannot just use the Coulomb's law and Biot-Savitz's law. Okay. So we needed to really to solve these whole equations. They are often very difficult to solve. Okay, so we needed to wanted to simplify it. Okay, so the way we often to do it, remember that for this electrostatic case, we introduced this potential function, a scalar function. Okay, we call it a scalar potential. And then for the magnetostatics, we introduced this vector potential. Okay. So now we wanted to see that, if we can solve this, make the calculations easier. Okay. So now let us look at this. Okay. So we have to, because now it's a time dependent ones, so we have to really look at these equations. What do we learn from these electrostatic and magnetostatic ones may not really work here. So now let us look at the first one. We have this equation, del dot B equals to 0. Okay, so this is really just to say this vector B will have this this divergence equals to 0. Because of that, we can always write down this. We can introduce a vector potential, okay, and A, and we write it down B equals to del cross A, okay. So any function of A, okay, if we write it down B this way, del dot B will be 0, okay. Remember for the electrostatic case, we have del cross E is equals to 0. Okay. Remember there, we said that the electric field, for this electrostatic case, doesn't do work. So that we can define a potential, we can define E as minus delta V. Okay. So however, now for this electrodynamic case, del cross E is not 0 anymore. Okay, it's equals to minus partial B over partial T. Okay, so that means we cannot define E as this, because if we define this, del cross E will be 0. Okay, which is certainly not the case. So then how do we do that? We can just do some tricks here. So you see del cross E, because B is now del cross A now. Okay, and because this is a derivative with two positions, this is with versus time, we can move this around. So we have this. Okay, and here we can really write del cross E plus partial A over partial T equals to 0. Okay, so this is what we have. So now you can see from here. Okay, so now this whole thing, del cross the core of this is 0. So what does that mean? We can really write this whole stuff as, for example, minus delta V. Okay, we introduce a new scalar function. Okay, and we write down this whole thing as this. Okay, and then of course, once we have this, del cross this will automatically to be 0. So in other words, that we write down here is del V minus partial A over partial T. Okay. So now you can see that we originally wanted to do E and B. Okay, we wanted to figure out the E and B. Now we replace this B with A, and we replace this E. Basically, now is V and A. Okay. Okay. So now we look at the two equations. So what about the other two equations? Okay. So now we wanted to, so we wanted to find E and B, and we replaced it with A and V. Now we needed to figure out what are the equations for A and V, and we solve them. Okay. Now we look at the other two equations. One is this. Okay. Okay. So this is, I put a minus sign there because I wanted to put it, because there are minus sign here. I wanted just to let it become positive. Okay, so it looks like this, partial T. Okay, so now del dot A, because I put a minus sign here, so it's rho divided by epsilon 0. Okay, so now V and A will satisfy this equation. Okay, so this is what happened for this equation. Now we look at the last equation here. Okay, so the last equation is a little bit more complicated. Okay, so if you look at the lecture note, I derive it. Okay, but here I just write it down here. So it looks like this. So you need to use some of these vector analysis formulas there. Okay, so it looks like okay, so it is a very complicated equation now. It looks like this. So here, so as I said, now we need to find A and V. Okay, so A and V really satisfy these equations. Okay, so there are a lot of formulas here. Okay, so it satisfies this. Okay, so it's really now we just need to solve these two equations, to figure out A and V. Once we know A and V, we can figure out the E and B. Okay, so in other ways that these two equations, the two that I showed here, they are really containing all the information in Maxwell's equation, but it's just a little bit a strange way. But these are really they are also Maxwell's equation, but just written in a different way. Okay. Okay. But you can see from problems here, you may see that this equations becomes even more complicated. Okay. Okay. So then we need to simplify this. Okay. So this is the so-called gauge transformations. Okay. So remember that we wanted to figure out the E and B. Each one has three components, X, Y, Z. So in total, there are 6 unknowns. Okay. Later, we converted to V and A. V is a scalar function, which is only one component. And A has 3 components. So here, in other words, we have 4 components. Okay. Okay. However, the equations here, that B and the E here, they don't uniquely define the vector potentials and the scalar potentials. For example, if we have V equals to V plus 5, for example, put a constant there, okay, del dot V doesn't change. Okay, you can see from here. If you put a constant for the V, it doesn't change. If you put a constant for A, for example, it also doesn't change the overall picture. So in other words, that there are some freedoms, on this V and the choices of V and A. So that really means that we are free to impose some extra conditions on this V and A, as long as nothing happens to E and B. Okay, as I said, if you increase this V by a constant number, it will not change E and B values. Okay. So now let us consider I have one choice, which is V and A. I have another choice, V prime and A prime. And we want to figure out, what kind of relation that we have between this V and A, so that they still corresponding to the same E and B. Okay. Okay. So let us consider, as I said, let us consider this A, the new A is really the old A plus some function. Okay, it doesn't need to be constant, but some function alpha. Okay. So V prime is also V plus some beta. Beta also doesn't need to be a constant. Okay, but it's some function. Okay. So now let us look at what are the conditions that we will have on this alpha and beta. So as we said, it should give us the same condition. Okay, so that means del cross A prime should equal to del cross A. These are Maxwell's equations, should give us 0. Okay, so from here we derived del cross this alpha. Okay, we cannot randomly choose any alpha. Okay, it has to satisfy this condition. Okay, because it satisfies this condition, we can really write it down as a the divergent of another function lambda. Okay. Okay, so alpha cannot be any function, any vector. So it has to be the divergent, the gradient of a scalar function. Okay, so this is what it tells us. Okay. Now, so this is a B. Okay, so the E, as we said, is really delta V minus partial A over partial T. Okay, and as we said, the new set of A prime, V prime should also give us the same electric field. So it should look like this. Okay, so now you plug this into this equation. Okay, and you will find that you cannot randomly choose alpha and beta. Okay, it has to satisfy this condition. Okay, you cannot randomly choose. Okay, so because alpha is really becomes the gradient of function lambda. Okay, then we will find that this one really means beta plus partial lambda over partial t equals to 0. Okay, so in other words, that because this is a derivative, so this is really means beta plus partial lambda over partial t is independent of position. Okay, because it's a derivative to the position, should be always 0. Okay, so that is what we have. So from here, so that means this should be only as a function of time or a constant, for example. So in other words, that this beta, these whole things should be a constant or some function that depends on t. Okay, so this whole thing, if you move to this side, you have kt. Okay, it doesn't depend on the position. Okay, so it can be a constant. Okay, so you can see that. So what does that mean? So that really means that we cannot choose any function of alpha or any vector of alpha. It has to be gradient of a scalar function, and then we cannot choose any any function of beta, and this beta has to satisfy this condition. Okay, so that is what we have. Okay, so now, okay, so this is what we have. Okay, so you can see that this beta and lambda, they are related to each other. It cannot be any functions. Okay, so we can, because we don't like this kt here. Okay, we can define a new lambda equals to, let us say, to the old one, this old one. Okay, and which is really, here I still use the lambda here. Okay, this is really just becomes the derivative kt prime dt prime. Okay, I need to have a derivative because here is just derivative with respect to time. So here I need to integrate it. Okay, so let us call it, this is a new lambda. Okay, this is called a new lambda. Okay, so then what we have is that so the new a should be related to the old a plus a function delta lambda. Okay, and this new v prime is should be this v minus partial lambda over partial t. Okay. Okay, so in this sense, I can get rid of beta, and I only have another function of lambda. Okay, so now, so that really means that now, when if I have a and I have a v, so I have a freedom to choose any function of lambda. Okay, as long as my new a prime is really the old a, the new a is really the old a plus the divergent, the gradient of this function lambda, then the b field will not change. Okay, so the same thing if the new scalar function equals to the old scalar function minus this partial lambda over partial t. If that is the case, then the electric field will also not change. Okay, so that really means at the end is really equals to the same electric field and also the same magnetic field. Okay, so this is what we call the gauge transformation. Okay, so you see that we have the freedom, okay, to choose A and V. Okay, there is a freedom for any function of a scalar function lambda. Okay, then if you satisfy these conditions, okay, it will not change the results. Okay. Okay, so that means we have freedom to choose this A. Okay, so that there are often, so this is what we call the gauge. Okay, so there one is called a Coulomb gauge. Okay, so remember the equations, this, as I said, this really becomes the new Maxwell's equation. Okay, so now it's just written with this A and a V. Okay, however, this whole thing, this equation becomes very complicated. Okay, so but we have the freedom to choose this A and also choose the V. So for this Coulomb gauge, okay, we choose del dot A equals to 0. Okay, so now if you see that if we choose that, and the first equation is very simple. Okay, so there are two equations now. Okay, as I said, one is this equation, one is this equation. So if we choose del dot A equals to 0, so this one becomes 0, and then we really have this Laplace equation. And here, of course, this one is simplified to 0, but we still have three other terms. Okay. So from here, we have this rho divided by epsilon 0. Okay, so then from here, we know it's Laplace equation, and we really have this Coulomb's law. Okay, we can really write it down. This is the charge distribution. This is the position vector. Okay, sorry. Then d top prime. Okay, so this is really just the Coulomb's law, for this potential calculation. So this one is fine. It's very easy to figure out the V. However, it's difficult to find the A. Okay, as I mentioned before, if you put the A equation, it will look like this: partial A so it becomes this mu 0 j plus mu 0 epsilon 0 del partial V over partial T. Okay, so you see that you can relatively easily find a V. However, it's still a very complicated function to really figure out the vector potential A. Okay, so then there is another option called Lorentz gauge. Okay, so here we can choose del dot A equals to minus mu 0 epsilon 0 partial V over partial T. Okay, so here we can choose this. So the reason we wanted to choose this, you can see that. So here is delta dot A plus this. So if we choose this one equals to minus of this, of course, we can get rid of this term. Okay. So now, if we do that, we can just plug into these two equations. What do you find that? So now the two equations will look like this. So it becomes like this. And you may see that these two equations, they look very similar. Okay, you see that one is the equation for A that is related to the current. Then here is the V that are related to the charge. So now if we define a symbol, this is square, okay, if we call it D'Alembert, okay, if we define it as this vector, mu 0 epsilon 0 partial square over partial t square. So this is just a symbol, okay, it's an operate. It has to apply on something to be meaningful, okay. Now, once you have this, what do you see here? Okay, so it just becomes like this. One very important thing from this picture, you can see that V and A are really treated on an equal footing. You know, their equations are really very similar to each other. You see that? And the left side is really, you know, this kind of, you know, the wave equation ones. Okay, you know, this is real. If you remember the wave equation that we have is really this. Okay, so in other words, that if there are no current, no charge, you know, this becomes zero. So A and V, they both satisfy the wave equations. Okay, and of course, if J and V and rho, they are not zero, so it really means A and V, they satisfy, you know, this inhomogeneous wave equations. Okay, and this J and rho is really indicate, you know, is a source. Okay, you know, like a wave source that create A, create V. Okay, and you can see that, you know, this whole electrodynamics now really reduced to the problem of solving this inhomogeneous wave equation, you know, for a specified source, for either for the current and or for the charge. Okay, so now you can see that you know, these two equations actually, you know, is really a very beautiful way to really write down the Maxwell's equation. Okay, so in some sense, you know, Maxwell's equation now in some sense becomes like this. Okay, and you can really see from here that there are a lot of symmetries, okay, between the electric field and also the magnetic field. Okay, and you know, these equations, you know, is very similar to the equations that are put on the cover of this Griffin's book. I personally think that you know, they should really replace, you know, the cover really uses this del, and I personally think it should be replaced by this square. Okay, because this is really, you know, indicate the symmetries, okay, between the electric field and also the magnetic field. And at the end, as I said, you know, this using this Lorentz gauge, that V and A, they are treated on equal footing, and then is really just needed to solve this inhomogeneous, okay, because often this is non-zero. So this is really inhomogeneous wave equations. Okay, we just needed to have some need to know this is specified sources, okay, for the current and for the charge. Okay, and here I hope you can see, you know, the beauties of this electrodynamics. Okay, the symmetries between electric field and the magnetic field, and this Lorentz gauge, you know, is the one that that is commonly used. And I would also say that you know, you will be able to learn more about this when you take a graduate level